We got some homework for you for tomorrow here, guys. Page 428. And the questions that I want you to do are questions 1 to 4. And 6 to 7. We'll give you a few minutes to work on those questions now, but probably only about 6 to 7 minutes. So see what you can do. Ask me some questions, and then take the rest of them home tonight. We just saw 2 videos that describe the Doppler effect. One was a definition that Sheldon from Big Bang Theory gave us. The other one was an actual demonstration of a police car going by us. Sheldon's definition said the Doppler effect is the apparent change in frequency, in other words, change in pitch, due to the relative motion of the source of a sound and the observer. Now, that doesn't make a whole lot of sense to most of us when we hear that for the first time. But when we actually hear a police car going by us and we have it described as the Doppler effect, then it maybe makes some more sense. Okay, as the police car is approaching us, of course it's getting louder. It's really not getting louder, right? It's just getting closer to us, of course, which makes it seem like it's louder, right? If I yell at you from 5 feet away, it's going to be a lot louder than if I yell at you from across the football field, right? Okay, it seems louder the closer you are. But what's really neat about that is that you also change pitch. Okay, as the police car is coming towards us, it's not actually, the pitch that we hear isn't actually the frequency of the sound that's made. It's higher. We perceive it higher than it's really being produced. It's not higher, we just perceive it as higher. Now, as it's going away from us, we perceive it as lower than the actual frequency at which it actually exists. So, as it goes by us, we hear that sound where it's changing almost instantly from a higher pitch to a lower pitch. You've seen that before. You've noticed that before when a police car goes by you, when an ambulance goes by you, when a fire truck goes by you. But also even when you're standing on the side of the highway and cars go by you. Even when they're not sounding their horn, there's a sound that's produced, a natural or resonant frequency that's produced when the car tires are on the road. You hear that car. But as it's going towards you, it actually sounds as a higher pitch than it really is. As it goes by you, it becomes a lower pitch than it really is. So we'll go back to the definition. I couldn't give a better definition myself if I wanted to, so we'll steal Sheldon's here. He said it's the apparent change in frequency of a wave due to the relative motion of the source and the observer. In other words, if you got something making a sound and something observing that sound, and one of those objects is moving, either the source or the observer, then what you perceive, what the observer perceives as the sound, is going to be a different pitch than what it really is. It's not a real change in frequency. Okay, frequency doesn't change. Once a wave has been made, the frequency of the wave stays the same. But it seems like it's higher or lower. If it's coming towards you, the pitch seems higher. If it's going away from you, the pitch seems lower. Now, why does that really happen? Why does it happen? Well, let's draw a little picture here, okay? Let's say we've got a source right here. We've got an observer over here. So the guy over here, the stick man, is the observer of the sound. The source of the sound is this dot. Maybe it's a horn, maybe it's a siren, maybe it's just the wheels against the road. Okay, it doesn't matter. There's going to be a wave produced that's going to go out from that source. Okay, and it's going to go out in all directions from that source, essentially in a circle. Okay, does that make sense? Now, let's zoom forward in time, let's say 1 second. 1 second down the road, this source isn't going to be in the same place. Okay, 1 second down the road, this source, oops, didn't want to erase the whole thing. The source is going to be right here because it's moving, let's say in this case, toward the observer. Now, that first wave that's produced is bigger now. So this first wave that I have drawn here becomes this wave. But my source, remember, is right here because my source has traveled kind of along with the wave. Now it's going to produce another wave, produces a second wave. The second wave is going to look like this. Now you can imagine if we kept drawing these, then we would find that there would be a whole bunch of wave fronts in front of the producer that would be close together, and a whole bunch of wave fronts behind the producer that are further apart. Now if I'm standing right here, Okay, if I'm the observer standing right here, and this object, this source, is traveling towards me, what am I going to hear? I'm going to hear a wavefront, 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 really quickly, in quick succession. Okay, that makes me perceive a higher frequency than is really there. If I'm standing over here, now this source is going away from me, right? As it goes away from me, what do I hear? Well, the wavefronts are further away from each other. So I hear wavefront, wavefront, wavefront in slower succession. So when I'm standing over here, they're closer together, I hear them quicker. Wave, wave, wave. When I'm standing back here, they're further apart, so I hear them slower. Wave, wave, wave. That's why I perceive a higher pitch right here, and I perceive a lower pitch right there. Does that make sense? You guys have all heard this before, right? Okay, the Doppler effect isn't new to us. Just the description of why it happens and putting a name to it is a little bit new, as is the equation, which is the last equation we do in Physics 20, but arguably the ugliest equation we do in Physics 20. There's a number of variables here, and they're a little bit confusing. In addition, we have this whole plus minus thing on the bottom, whatever that means. FD is going to stand for the Doppler frequency. The Doppler frequency is the perceived frequency, the apparent frequency. That's what we hear. So if a car is coming towards us, blowing its horn, and the pitch of that horn is 500 hertz, we would perceive it as maybe 600 hertz. The Doppler frequency, FD, would be that 600 hertz perceived frequency, not the real frequency, the perceived frequency. FS stands for the actual frequency, or the frequency of the source. So if the car is coming towards us again with a frequency of 500 hertz, we hear 600 hertz, FD would be 600, and then FS would be 500, the real frequency of that car. These are the ones that are a little bit confusing, okay, if that's not already confusing. VW and VS. It's confusing because VS, most people would look at this and think VS is going to be the speed of sound, but it isn't. VW is actually the speed of the sound. We're going to call it the speed of the wave, though, which is usually sound, but not always. The reason we call it VW instead of VS is because it's not always sound. It's just usually sound. VS is going to be the speed of the source. So maybe the sound is traveling at 340 meters per second that a fire engine produces. Okay, that would be VW. The fire engine is traveling at 30 meters per second. That would be VS, the speed of the object making the sound, VS. So the sound itself, VW, the speed of what's making the sound, VS. What is always going to be the smaller number, VW or VS, the speed of the sound or the speed of the source? Speed of the source. Okay, if you're traveling, if you've got a situation where the object that's producing the sound is traveling at faster than the speed of sound, then you've got other effects other than the Doppler effect taking place. Okay, you hear what's called anybody know what you hear? It's not the Doppler effect. You hear a sonic boom. If the source is traveling faster than the sound itself. And I'll explain that after we've gone through this a little bit as well. All right? Okay. Done? No. The ugliest part of it is this whole plus minus thing, although it doesn't have to be the ugliest part of it. We can never have an equation where we use the plus and the minus at the same time. It's either going to be plus or it's going to be minus at any given time. So it might be VW plus VS, or it might be VW minus VS. Depends on the situation. But it's not going to be both. So when is it plus? When is it minus? I told you guys when we were going over the stuff before, I said, look, don't remember these equations because you'll forget them, just like me. Okay, I never remember, to this day, I never remember when this is supposed to be plus and minus. Okay, if you give me 1 second to think about this right now, I won't be able to tell you right now whether it should be plus or minus in what situation. Okay, but if you give me 5 or 6 seconds to think about it, to work through it in my head, then I'll be able to figure it out. Not because I remember it, not because I'm digging back into the recesses of my mind to try to remember it, but because every single time I do this, I figure it out. And I'm going to figure it out, truly, I'm going to figure it out right now with you. I don't remember what the answer to this is. I'm going to figure it out with you, and that's exactly what I want you to do every single time. Because you're better off that way, right? You're not going to make a mistake if you're figuring it out. You're going to make the mistake if you're trying to remember it. Okay, so here's the logic that we use here to figure this out. The Doppler frequency will be higher when the objects are coming together, right? Okay, the Doppler frequency will be higher if, let's say that John is the fire truck, he's making the sound, okay? I'm the observer, John's coming towards me, the fire truck is coming towards me. I'm going to hear a Doppler frequency higher than the actual frequency. Do you agree with that? Okay, so it's going to be a plus or a minus when the observer and the source are moving away from each other and when they're moving towards each other. John's moving towards me right now. The source is moving towards me right now. Do we make it a plus or a minus? Well, we know that we have to get a higher Doppler frequency. FD has to be bigger than FS. How do we make FD bigger than FS? Well, we have to have a number on the bottom that is smaller, okay? If you want to get a bigger FD than FS, then the number on the bottom must be smaller. Does that make sense? Okay, let's say VW is 10. Okay, let's say the number on the bottom is 2. Okay, that gives us 5. Let's say the VW is 10 and the number on the bottom is 4. This gives me 2.5 on the bottom. Sorry, 2.5, right? So if you make the number on the bottom smaller, then we're going to make the overall number bigger. We want to make the overall number bigger if John is coming towards me. So that means as John is coming towards me, these two numbers on the bottom have to be subtracted from one another. As they move towards each other, you want to make the plus/minus negative, or a minus. So it becomes VW minus VS. It gives me a smaller denominator, which gives me a bigger FD. Fire truck turns around, goes away from me. What do I hear? Okay, if the actual frequency of the sound that John's making is 500 hertz, maybe now I hear 470 hertz. Okay, if I hear 470, that's a lower FD. If I hear a lower FD, that's going to come from getting a bigger denominator down here. That means when they're moving away from each other, we're going to make that plus or minus positive. Listen, guys, I'm not exaggerating when I told you that I don't remember which one's which. Okay, when I wrote those down, when I was working through that logic with you, I was figuring it out. Okay, I probably could remember it if I tried. But my take on it is, why should I bother trying? Because if I try, then I'll probably get it mixed up at some point. If I figure it out, then I almost can't get it mixed up, as long as I'm pretty good in math, right? And recognize that a smaller number on the bottom gives me a bigger number over here. I almost can't mix it up. There's a lot to this, right? Okay, there's a lot to this mathematically. Good news and bad news. The bad news is sometimes you guys aren't the greatest at rearranging equations. And let me tell you, if you want to solve for VS here, or VW, it's brutal. It's brutal to rearrange to solve for VS and VW. Now, do you want the good news? Good news? The good news is we won't make you do that. Okay, the good news is we'll make you solve for either FD, the Doppler frequency, given everything else, or we'll make you solve for FS, the actual frequency, given everything else. And both of those are relatively pretty easy to solve for, right? A little bit of rearranging, but not much. Yep. No, no, be careful with that. This is a very special form of the equation, actually. The actual Doppler effect equation is a little bit more complicated than this, if you can believe that. It's more complicated than this. Okay, this equation is assuming that the object that's making the sound is moving toward or away from a stationary observer. Does that make sense? Now, if we wanted to make both of them moving or some other scenario, we'd have to have a different form of the equation. So this one doesn't work. Okay? So don't try to change things around a little bit. It just doesn't work. Now, it doesn't look all that different, the general form of the equation, but it looks a little bit different. And this is hard enough to deal with, right? We've got a Vs that we think is the speed of sound, but it's not. Okay? Vw is the speed of sound. And then we try to remember what's positive and what's negative and whatever. This one's hard enough. If we use the general form, it's even harder. Let's take a look at this example in 432, please. So it says a train is traveling at a speed of 30 meters per second. Its whistle generates a sound of 224 hertz. Okay, what am I dealing with here? This is a speed, clearly. Is this going to be Vs or is this Vw? Vs is the speed of the source. Good. So it is going to be Vs. Okay, Vw would be the speed of the wave, and we don't know how fast the sound is moving here right now. Not yet, anyways. 224 hertz. FD or FS? The Doppler frequency or the actual frequency? Real? Yeah, it makes a sound at 224 hertz. This is going to be the actual frequency. This is going to be the frequency of the source. We're standing beside the tracks as the train passes by us. What change in frequency to detect for the pitch of the whistle as the train passes if the speed of sound is 330 meters per second? This is going to be VW. Believe it or not, guys, we'll spend some time between now and the end of classes doing a little bit of review and checking over some homework and that sort of stuff. But this is your last example problem that we do this year. We saved a good one, though, to do for your last example problem. If you think that equation is challenging, and it is, this question is actually even more challenging because we're not asking for the Doppler frequency. We're asking for the change in frequency. What do we got to do? What do we have to do to find the change? John? Good. Good. Find the Doppler frequency as it's approaching. Find the Doppler frequency as it's going past us, as it's going away from us. And then what do we got to do with that? Then we got to subtract it too. So it's not that much harder, right? Mathematically, it's twice as much work. Not that much harder conceptually, once we kind of get the hang of it, right? So let's do that. Let's do that now. Let's say, first, it's approaching. What was the equation? We said FD is equal to VW over VW plus or minus VS. What was it? As they're coming closer together, as John was coming closer to me making the sound, was it a plus or a minus on the bottom? It's a minus, right? We need a bigger FD. That means we need a smaller number on the bottom. Okay, we multiply that by FS. So it's going to be VW, 330, divided by 330 minus 224. No, that's wrong. 330 minus 30 times Fs. And Fs is 224 hertz. So let's get that number. Okay, let's do it on the calculator here because it's a little bit tricky. get the number on the bottom first. 330 minus 30 is 300. Easy enough, right? So let's say 330 divided by 300 equals, and then let's multiply it by 224. 246.4. You know how we know that we were right with this? You know how we know that we made it a negative correctly instead of incorrectly? How we know that we shouldn't have made it a positive? Joe? We got a bigger number. Okay, the source is approaching us, so we should get a bigger number, and that's what we got. Now we're going to say that it's receding. Receding just means that it's going away from us. Okay, the source is receding away from us. Same equation, almost. What's it going to be here? VW over VW plus VS. It's going to be the opposite. Looks almost identical, but we're going to get a different number here. 330 over 330 plus 30 times 224 equals, that's going to be 330 over 360. Multiply that by 224. Gives us, why did I do that? I don't know why I did that. So what do we got? 0.916666. Let's do that again. Times it by 224. 205.333. How do we know that we have the right one this time? Plus or minus? We got a lower one, right? It's receding. It's going away from us. We should get a lower one. Now, do you want to find the change in frequency? It's going to be final minus initial. 205.3 hertz minus 246.4 hertz. Which gives us what? Negative 41.1? Is that right? So as that train goes by us, and we hear that typical sound of it approaching us and the typical sound of it going away from us, the change in frequency, the perceived change in frequency, because the real frequency doesn't change, the perceived change in frequency is 41 hertz. It's quite a bit, and that's why you notice it, right? I'd like you to take a look now at the practice problems on page 432. If you're opening up your own book to page 432, you're going to notice there's 4 questions on it. Okay, I don't want you to do the last 2 questions, because the last 2 questions, if I remember correctly, involve both of the objects moving. Either that or solving for VW or VS, which I told you won't have to solve for. So if you can do 1 and 2, you're probably in pretty good shape here for what you're going to need to do for your test coming up on Thursday, right? Give you a few minutes to work on those now.